if we look at this quadratic equation, this here, we've seen already in the drill, is a quadratic expression, the left-hand side. So if I ignore this part of it, that's a quadratic expression. It's quadratic because it's got a square term. It's also got a linear term and a constant. It wouldn't have to have this linear term or the constant. The fact that it's x squared makes it quadratic. So this is as long as a quadratic we could have. This is, in fact, what's called a power function with the highest power of x as x squared. We can have x cubed, x to the 4, x to the 5, and the longer they are, the more difficult they are to solve if we want to try and solve this equation, for example. So I'll make it into an equation by saying this left-hand side equals 0. And you might remember from last year that to solve this, we have to have the right-hand side equal to 0. And then we have what's called the general quadratic, where a, b, and c are constants, and they are the coefficients of x and x squared. So a is the coefficient of x squared, b is the coefficient of x, and c is a constant that's there as well. So this is taking into account all possible quadratics, isn't it? Because a, b, and c can take any value, including 0. If you solve this, and in the textbook, if you're interested, it takes you through how this is solved for x. And x turns out to be minus b plus or minus the square root. Note the plus or minus, that comes from the fact that when you take a root, the answer can either be positive or negative. B squared minus 4ac all over 2a. And you might be familiar with that formula. And that's the solution to this. This is the solution to this, where the right-hand side is 0. So all I have to do, a bit like that volume formula we had a minute ago, is just plug in the values for a, b, and c, and out comes the answer. And you can do it in one hit on the calculator. I can put all this on top of the fraction using the fraction button over here. That fraction button. So put all this on the top, minus whatever b is, so minus 2, plus or minus. I can't put plus and minus into the calculator at the same time, so I just put the plus in, and then later on I change it for the minus. Square root of, and then put all this inside the square root, divided by 2a. And so that's what we tend to do. So for this particular case, x equals minus 2 plus or minus the square root of minus 2 squared minus 2 squared, what am I saying? 2 squared minus 4 times a, which is 4, times c, which is 3, divided by 2 times a, which is 4. So I'd probably do that, and then I get my calculator out. I might even work out what that is. 4 4s are 16, times 3 is 48, thank you. So x equals minus 2 plus or minus the square root of 4 minus 48 all over 8. What's 4 minus 48? Minus 44 over 8. Do that on the calculator, what happens? Yeah, doesn't like it. Why doesn't the calculator like it? Yes, which is, yeah, well done. You cannot have the square root of a negative number. This is impossible. That's what the Greeks asked themselves. What we're going to do then? We can't do it. There's no such thing as the square root of a negative number. And of course that was a problem. And mathematicians of the time, just like would be today, don't like problems you can't solve, and they look around for ways to get round it. The problem is this. Okay? The problem is this bit only, the negative sign. So let's go as far as we can. First of all, if I've got a fraction with something plus or minus something else over 8, I can split it. I can say x equals minus 2 over 8 plus or minus the square root of minus 44 over 8. I could do that bit. Minus 2 over 8 is a quarter. Yeah. Now, if we think about this, if I've got, as a little aside here, the square root of something like, say, 4 times 9, which is the square root of 9, 18, 27, 36, I can split the square root of that into 4 times 9, which is the same as the square root of 4 times the square root of 9. I could split it and square it each bit separately, which is 2 times 3, which is 6. What's the square root of 4 times 9, 36? 6, same answer. So I can go one step further. I can say, okay, the only bit that's difficult about this is minus a quarter, plus or minus the square root of, let's do this. Let's split the minus 44 into minus 1 times 44. And yeah, why not? Because minus 1 times 44 is minus 44. So then I can say that means x equals minus a quarter plus or minus the square root of minus 1 times the square root of 44 over 8. Well, I can do the square root of 44 on the calculator, because that's positive. What is the square root of 44? 6 point something, isn't it? .7. Sorry. 6.63 times 6.63 over 8. Yeah. So if we look at this now, we can actually work out what 6.63 divided by 8 is. We can do that bit, that divided by that. What 6.63 divided by 8? 0.82 times the square root of minus 1. So actually we're getting pretty well on the way now. The only problem is this. And if you think about it, it wouldn't matter what this number was inside the square root here. I could always split it into minus 1. If it was a negative number, I could always call it minus 1 times whatever this number is, couldn't I? Whatever it was. So in any problem that we're going to have where we've got this negative coming into the root, we can do everything apart from this bit. So this is where the Greeks came along and thought, well, let's just call that a letter, call it something, because it cannot possibly exist, this square root of minus 1. They call that the imaginary number. Yeah. Now, it turns out that although this was invented to get around this problem, the geometry that's involved with this Cartesian geometry that's involved with these quadratics, turn out that you can actually, in the real world nowadays, the theoretical physics that's going on, actually have discovered in a way that these really do exist, these imaginary numbers. And they can be used in space-time problems. Yeah, and I don't profess to understand that at all, but I just do know. Okay, so why are we doing it here? Because there's another way that we can use these things. What we do is, and they come in really handy in engineering, what we do is we say, okay, we're going to call this the imaginary number, and the mathematicians call it I for imaginary number. But the engineers, because we use I for current, and they use imaginary numbers all the time in electronics, they don't use I, because it will confuse with current, they use J. And you might have come across this J term. J, in an engineering environment, means the imaginary number. And J equals the square root of minus 1. So it's undefinable. We can't work out what that is, so we just leave it like that. If we think about what a square root is, think about the square root of 4, which is 2. Listening. Think about the square root of 4, which is 2. The square root of a number, which is the number, if we multiply itself, we get 2. Don't. Square root of 2 is the number, which times it by itself gives me 2. So if I square j, whatever the square root of minus 1 is, if I multiply it by itself, it gives me minus 1. So what's j squared? Not 1. Minus 1. Whatever that square root, whatever that number is, which doesn't exist in the real world, it's an imaginary number, if I square it, I get back to minus 1 because of the definition. So that's important. That j is the square root of minus 1, which means that j squared is minus 1. So if I end up with squaring j's, these imaginary numbers, I get back to the real world effectively, because minus 1 is a number. So it's only imaginary, it's only impossible, if you like, when it's j. So what can we use this for this final answer? We can do this. We can say that x equals minus a quarter plus or minus 0.82j. And that would be our answer, where j is the square root of minus 1. Now this is where it comes in useful in engineering, because this is called a complex number. And it's got a real part. In other words, that's a number, minus a quarter, and an imaginary part, because that's got this j associated with it. And together, the real part and the imaginary part in here make up what's called a complex number. So the whole thing is a complex number. And they arise from trying to solve quadratic equations where the root is negative, and means you can then come up with an answer. Now, why it's important is because we can use it to represent vectors. What we do is we use our coordinate system, the rectangular coordinate system, which we looked at already, but instead of calling this the x-axis, we put the real part of the number along that axis. So we put the quarter along here somewhere, and we put the imaginary part of the number on here. So this is the imaginary axis, which means we could represent the complex number as a vector. If we look at this problem, it could be there, quarter along there, and 0.82 up the imaginary axis. But because it could be positive or negative, we actually have two possible answers, one positive and one negative. But they're vectors. And what we're going to look at in a minute is how we can represent these complex numbers on these systems more accurately, and then how can we add, subtract, multiply and divide these complex numbers here, because then that means we've got a quick way of adding, subtracting, multiplying and dividing vectors like forces or voltages and currents in circuits. And that's where it comes in really useful in engineering. Okay, I'll stop